Professor Shenlong Wang from University of Illinois, who has prior experience from self-driving car Uber. So his expertise is in computer vision and robotics. His research focuses on creating a digital replica of the world and simulating realistic new content to train and validate autonomous systems. His past work received ACRL-UIUC's Best Application Paper runner-up and CVPR Best Paper candidate status. His contributions to autonomy in simulation have led to 25 patents. He has received NSF Career Award, Amazon Research Award, various fellowships from Facebook, Adobe, and Royal Bank of Canada. So Shenlong, with that, it's an honor for me to have you. And we have turned on the recording already and we'll basically share it publicly to publicize your work. Go ahead.
Sounds good. Thank you, Nara, for the introduction, and thank you for having me here. Today, I'm going to talk about my group's recent research on digitizing and simulating the 3D physical world with some of our applications to self-driving autonomy. So let me start about what do I mean by digitizing and simulating the physical world. And here is an image about a nice German town that likely to take in a summer afternoon. Just for your information, this is actually one of the frame of the video that in the famous Kitty dataset, one of the earliest and most influential self-driving dataset. So by taking this image, we can understand that it's an empty street. There are a few cars, and it's like a small little town with just residential buildings and so on and so forth, right? And this is our capacity about understanding the visual content. And that being said, for humans, we have another capacity. That is, we are able to, based on whatever our observations, we can ask some of the what if questions. For instance, like here we have been showing a summer image and at the daytime. So what if it has been taken at nighttime, right? What if the car is driving at night, right? We could potentially imagine what's like, right? Something like that, right? The town is dark, the street light is on. Potentially, if we take a photo from car's perspective, we might also see the closed area to be lit by our headlight and so on and so forth, right? How about what if the empty street become more crowded with people, right? We could also have some capacities in terms of imagining what's going on if there are some of the people present or some of the other obstacles like traffic cone here, right? Say here is also sunny weather. What if it's basically driving in a heavily smoky day, right? What does it look like? Or even a sandstorm, right? So with our mind, once we close our eyes and just imagine a little bit, it's not really hard for us also to get some of the mental pictures like that. Or the street is covered by snow, or even more extreme, what if the town gets flooded? We may imagine something like that, right? So those are some of the cases that might happen. I hope that it doesn't happen in this small little town, but it might happen in the real world. But our imagination is beyond what is some of the typical scenarios, right? What if I asked you, imagine for that small for that picture, right? What if there is a giant minion block the road, right? This is actually something that in self-driving we call it, corner cases or long tail events. Those are usually the events that is unlikely to happen, but once they happen, we might want to still ensure our self-driving autonomous system is safe and can handle those situations. It actually happens at least once, in the real world, that there's a big giant, minion that somehow falling on the street and block the road. And how about we imagine that to happen in our German town? That the answer is yes. We could also potentially do that, right? We human do have some of the capacities that allow us to perceive the physical world from our sensory observations, like from our eyes, from our audio sensory, and so on and so forth, so that we are able to build a mental world model about what is our surrounding world looking like. That is our perception capacity. I'm pretty sure that since the AVIAT is working on autonomy, there could be some, there must be some of the previous lectures cover some of the perception side of things. That being said, we also have another capacity that is within our mental world model. We are able to recreate new experience like what I showed before, and then reassemble them and augment our sensory observation and imagine something that didn't really happen, some of the counter scenarios that didn't really happen. So this is something that in cognitive science, people call it recreative mind, recreative imagination. Yeah, so it's formally speaking, it's a capacity that allow us to think about the world from a different perspective than what we have been experiencing at this moment. So in this talk, my goal is to make computers to be able to imagine in the physical world just like what humans do, and to build programs that can automatically do that based on sensory observation. Specifically, in today's talk, we focus on vision. And in fact, all those images I showed before are some of the output of some of the algorithms that I'm going to talk about later. All right. So firstly, let me talk about, why we care about recreative minds, right? Recreative mind seems like it can create some interesting or fun, visual experience. But why do we need that? Actually, here I want to bring everyone, memory back to the very classic autonomous system formulation, right? The agent and the environment interaction loop, right? This is on the right, I show a red block that is a real world. And then there is agent that is consistently interacting with this real world through observations and actions. Essentially, the agent can be humans, can be autonomous agent, can be a robot, or can be even just a thermostat, so long as it can observe the world from certain perspective and based on the observation, take certain actions in order to achieve some outcome or in order to optimize some outcome. That this is essentially the so-called the agent and environment interaction loop, right? Our goal is to build a capable autonomous agent that is able to interact with the world to achieve some of the goals, right? In self-driving, we want to achieve the goal that we navigate from A to B safely without colliding with others or without bringing anything that is dangerous, right? So in order to do that, we might want to need a lot of data to gain some experience to our agent or use that to verify the safety, verify the performance, and so on. So how about that? We'll just run the agent in the real world, say run maybe 100K different episodes, and then let's collect a lot of data, right? And we will use that data to train and test our agent, right? In the ideal world, yes, that is definitely doable, but in practice, there are a lot of challenges that actually make this very simple real-world closed-loop data collection to be hard, right? There are a few challenges. The one is this type of data collection might not be really safe in practice. For instance, when we develop a self-driving autonomous vehicle, right? So we might actually face this type of very classic situation about a pedestrian and the vehicle, they are interacting with each other, right? This is a very classic question that autonomy might ask itself, should I yield to the pedestrian or not, right? Making the wrong choice potentially will result in catastrophic failures. They might risk people's lives. They might cause a lot of, expenses and so on and so forth. So this having such a data collection without ensuring safety is quite risky and costly. And another classic example is if we want to train a surgical robot to do surgeries. I'm pretty sure that no one wants to be the first patient that been used to collect data for this surgical robot, right? This is also because of the fact that it's not safe. But there is another type of challenge that might happen in the real world. For instance, if our agent is policymaker, its observation is some of the past weather data and so on for the urban area of Chicago. We know that Chicago sometimes might suffer from urban flood, right? And then we might have some actions that maybe we can build a new underground infrastructure to mitigate the flood, right? Then it's valid to ask the question, what if, what will happen if I spend like $1 million to build a new underground infrastructure? That being said, answering this question might take a few decades because we will only see the consequence of the action after a long period of time. So ideally, we might want a time machine that can accelerate this, allow us to evaluate the consequence really fast than the real world pace, right? A third example is straightforward, right? So for a researcher, I'm really curious about whether my AI-based, autonomy model is safe to some of the large animals on the road. For instance, this elephant crossing the road. I hope that it never happens in Illinois, but once it happens, we need to make sure that our model is able to react properly. That being said, this type of scenario is too rare to collect in the real world or too costly to collect in the real world. So in order to fight against those type of obstacles in data collection for autonomy, we need recreative mind. So the idea here is we need recreative mind allow us to do a lot of rehearsals. So for instance, on the left is still the classic, action and perception loop on the left. That being said, on the right, if we are able to build a digital twin of our real world, and then in this digitized world, what we can do is we are able to rehearse different actions and see different observations, and also to get different expected outcomes. And whatever action that it happens in the twin world, it might result in a safety critical situations. It might cause it might have some hazardous results. That being said, everything happens and stays in the digital world. It does not really harm the real world. That being said, we are able to get expected outcome, and based on that expected outcome, we can choose potentially whatever the best actions that allow us to optimize our outcome in the real world. So I believe this is a merit about why simulation is helpful. Simulation helps in terms of creating many data, at a reduced cost than collecting them in the real world. And simulation helps in terms of help us to verify which potential agent or which potential actions is the best. All right, so far, so good. Any questions? By the way, I want this talk to be as interactive as possible, so feel free to interrupt and ask questions whenever you have. We don't have to wait until the end. All right, so far so good, then I will move on. Yeah. So now let's talk about what are the potential, ways to achieve the goal that we want to build essentially a recreative mind. So actually there are two different cultures here. So one culture is there is a buzzword called the world model. It actually coming from cognitive science, and it inspired by the human's capacity in terms of doing all kinds of like counterfactual reasonings and the imagination, right? The general idea is it has a lot of data with observation, sequential data and action pairs with observations. And we want to train a model that based on our past observation and based on one of the action, we want to predict what we'll observe in the next. So it's usually a model, and later on, machine learning community has adopted this similar idea, and they want to train a generative function that similarly take current observation and certain actions in and output the next observations. So generally speaking, this type of world model, often only predict observations, and there is no explicit state model of how the underlying world goes. And it just implicitly model that, and then take input observation and output new observations. So the other alternative is actually starting from the world of computer graphics. They leverage model-based knowledge to actually explicitly model how does this work. For instance, if we want to simulate physics, we have Newtonian physics, and we'll leverage those Newton rules to explicitly model how the underlying state has changed based on our input state and certain actions. And then we predict, what we predict is also the underlying state, and potentially we can use that state to generate some more observations, so rendering and so on. But the key idea is we'll use model-based knowledge rather than leveraging data-driven, method, and we'll explicitly model the state change. And interestingly, recently there are two works, both of the work I like a lot, by the way. So they all called Unicim, but essentially they represent the latest greatest. Or this might be giving a concrete example about how does these two culture looks like. On the left is a word model approach called Unicim. It's actually our best paper this year. So essentially, it takes a video sequence, egocentric video sequence as input, and then we'll just take one action. The action may be the person grasps the plate, and then it will predict the next short snippet where the person is actually grasping the plate. You can see that the input and output space is both video. It does not really explicitly model how the hand being moved there to grasp the plate and so on, and how the physics works in terms of friction and collision, grasping and so on and so forth. But the good news is they allow us to leverage tons of video data, directly learn such an input and output pair. The other way around is Unicim that coming from University of Toronto. So it's last year's APR work. It actually explicitly builds the 3D words and encodes geometry, encodes the appearance, and so on, encode the fact that how we are able to render from different perspectives, and encode the fact that the street has been composed about multiple cars. We can arbitrarily move each car into different location, basically change the state, and render correspondingly a photorealistic video footage. So this allows us to test our self-driving cars based on different actions of the car or based on different actions of the actors and so on and so forth, which is also quite nice. But as you can see, this is purely based on model-based knowledge, use implicit reasoning. In today's talk, most of my work has been advocating the second one for the reason that if we want to use simulation for autonomy, it's better for us to get some of the implicit state so that we are able to compute collision, we are able to evaluate how good our autonomy works, and so on and so forth. And also we can ground physics in order to close the sim to real gap. So next, I'm going to briefly talk about why I do believe, building a generative simulator at this moment is, I think it's timely to work on this type of digital twin modeling and simulation. So one big advantage so far in AI is generative models. It can create beautiful images. That being said, at this moment, most of the generative AI model still lacks of physical grounding and also lacks precise controllability, so that most of the generative AI approach cannot be used for closed loop training and evaluation yet. And on the other side, we do also have a lot of advances in terms of how we are able to perceive and model the 3D world based on sensory observations. One of the advantages is called neurosim models, which can actually establish a neural representation that allow us to represent a 3D scene, encode its appearance, geometry, and semantics, and so on and so forth. That being said, it has very limited editability. So that means it cannot enable counterfactual reasoning and generation. And in the world of computer graphics, people has been built physical simulation, but it all relies on artificial assets, and it's not based upon the real world. There is need a bridge that links the reality to the physical world. Yeah, for the sake of time, I might skip some of the prior work. But the key desired things will be realism, physical plausible, temporal coherent, closed loop, allow closed loop simulation, allow precise controllability, and everyone could be potentially the creator and could be potentially the user, right? Our approach, the key idea is to leverage data-driven method and model-based knowledge in order to simulate. That being said, our simulate is coming from the real world data rather than some user-created data, and also will use the simulator back to the real world and augment the reality. All right. So just a quick, background, a small background tutorial about one of the key methodology that we have been using throughout this talk is something called neural scene models. So the neural scene models represent a scene using a neural network, a deep neural network. So whose input is usually a location query, say a spatial location, say XYZ. And here specifically for this example, we also have viewing angle, query, basically 5-dimensional queries, and that output will be the colors. And this type of neural scene models enables, to encode the information into a deep neural network, right? So whenever we say for instance, in this nerve thing, so whenever we want to render image, we'll shoot out a ray for one of the pixel, right? And then we'll basically query different colors along this ray, and then accumulate those rays color and get our rendering color. And we'll learn this neural network by minimize the discrepancy between our rendered color and observed color. Once it has been minimized, this neural network is capable of rendering and replicate our observation. And what is even more interesting is because of the implicit structure of this network, it can allow us to render from a different perspective that we might never see from that view angle, but still can give us corresponding view angle. So that means it encodes the complete scene knowledge and information. And later on, people have extended that into encode not only just RGB color, but some of the physical properties, surface normal properties, geometry properties, semantic properties, and so on and so forth. And that being said, this type of vanilla neural radiance field or neural scene models, they can only encode whatever has been observed, but they cannot recreate. This is one of the gap that our group want to to achieve. For instance, can we actually simulate some weather hazard to the real world data that does not have hazardous weather, right? This is called climate nerve. So the motivation is that more than 20% of the vehicle accidents actually involves in those type of hazardous weather situations, right? So that being said, we don't really have a lot of data that to cover this type of hazardous weather, simply because it's too risky to collect those data in the real world, right? So what we want to do is, given some of the nominal weather situation and some of the weather input, say we want this nominal situation to be heavily snow after a blizzard, right? And what we will do is we build a scene model looking like that, right? It allows us to render from different perspectives and encode rich information about semantic and geometry and appearance of the scene. And then what we might want to do is, let's try to convert this scene into a winter-ish color, right? We know that generative AI nowadays is able to transfer the style of the image from one style to another. So we actually give a try of that. And what it ends up with is some of the video that are looking like that. You can see that it looks like a winter-ish thing in the sense that all the ground are whitish, but there's still something that is missing, right? What is missing is actually there is a lack of the real physical entities, which is the snow, right? So in order to compensate that, we actually run physical simulation and let the snowballs actually drop onto the scene, accumulate, and then render and compose together with the existing 3D scene. And that gave us our final rendering of this type of video that looking like this thing actually has been covered by snow. Of course, for different weather scenarios, for instance, like smoke or flood or snow, will use different representations. Like smoke will use the volume as a representation, and for flood we'll use a rippled surface, and then the ray will basically get reflected on the water surface, and then we need to curate in order to get the proper light transportation and so on and so forth. So here is some of the results. I will skip some of the details about the geometry. And then we can see that here is a video about what if this playground has been covered by light flood or more like heavier flood, or light snow, or heavy snow, or basically light smoke, or sometimes, we might have very heavy smoke and so on. So as you can see that this allow us to simulate hazardous weather into any, one of the videos. The reviewers asked us, what if, you simulate something that is different, like for instance, falling leaves and so on, right? We said it's actually quite straightforward because everything is physics based. And given the fact that it's physics based, it can generalize pretty much to every video. So here we can showcase a wide range of videos can be simulated under different weather effects and so on. And those weather effects are highly controllable. That means based on different severeness of the weather, we are able to control the corresponding effect. So another thing that we have learned is that this type of simulation is heavily dependent on the quality of the geometry reconstruction. Say, for novel view synthesis, we might find that two algorithms actually getting similar results on the leftmost, from leftmost figures. That being said, if we zoom in about the simulation, here I'm not sure whether we can see that from Zoom. So a lot of snow has been accumulated on the trunk of the tree. And this is not really practical in practice, because we know that the trunk of a tree is vertical to the ground and it shouldn't actually accumulate a lot of snows. The reason is just because the neural scene model actually learns to cheat because they don't have to get the perfect geometry in order to render well. That being said, in order to simulate well, we need to get a good geometry in order to reflect the scenes, the physical properties of the scene. So this is one of the take-home message that we have learned. And of course, we are able to simulate some of the extreme weather effects, assume that, say, everyone is driving SUVs in the next 50 years and our sea level has rise for Sydney Opera House. And I will skip some of the videos for the sake of time, but we can see that we are able to simulate extreme weather for driving scenarios like those little German town that I showed before. Okay, now we can definitely test how our self-driving perception will work for those type of extreme weathers. So here we showcase the results of a 3D object perception algorithm based on just a single monocular image. As you can see that those 3D object detection has been, given the fact that it had been trained on nominal data, it actually runs very well for those type of nominal situations. But as the weather becomes more and more severe, we can see that the performance of that object detector has degraded a lot, which suggests that this type of simulation could be a very good data augmentation in order to get our perception algorithm to be more robust to extreme weather. And for the sake of time, I will briefly showcase another type of physical, simulation that is basically changing from the daytime to nighttime. So here is some of the examples, which, this work is in principle very similar to the work that we showed before. So we model the 3D world, we understand some of the physics, and we alter the physics. Here we alter the lighting conditions. We simulate some of the light, like a street light and the headlight. And then we are able to relate the image and then get a new version. Here we also showcase that we are able to do precise control, like we turn on the street light one by one, and you can see the effect of the street light looks quite realistic. That being said, there are still a lot of work to go towards fully relatable 3D scene representation from a single monocular video. This is a quite challenging problem. All right, so here what we have been showing is essentially, say, for an existing video, how about we change some of the physical properties of the scene and then render it. It's actually not a real-time method. The very next question that we want to ask is, can we actually go further? That can we build the entire real-time interactive environment, just like a real-time simulator or even real-time game, right? So here is our problem formulation, right? Given a single video, still a video, say like a driving scene, our output is actually a real-time realistic interactive environment that allows everyone to, play, in real time in any devices so long as it support OpenGL and at a real-time frame rate. So for instance, on the left, we show some of the GTA-like game or basically Temple Run-like game, right? So the motivation is simple, right? We know that building a photorealistic simulator is important. That being said, building a photorealistic simulator, is also costly. Here is just a screenshot of a game, right? In this screenshot, everything in total costs around $200,000, which is more than 2 PhD student year at UIUC, right? So two of my PhD students started working on that in order to automate this process and allow us to build this type of 3D assets for simulation, but by taking just a single monocular video, right? Overall, our framework is by taking a single monocular video, we'll still build the neural scene models, which is like the space nerve. But this nerve is actually not something that is directly game compatible, as I discussed before, right? Most of my previous work that I show on the weather simulation and lighting simulation, it's all offline. It's not really something that is compatible with Unreal or Unity, those type of engines. So what we'll do is we'll basically bake this into explicit mesh-based representation that is compatible with games, and also identify different rigid body objects that is interactive with users and that can be interactable with the scenes as well. And also we'll bake those appearance into some of the OpenGL compatible texture map. And that allow us to build an interactive environment end-to-end automatically, and this is basically the overall pipeline. That being said, there is one big challenge lies in between. So the key is, in order to make the entire scene to be interactive, we should not only just identify, oh, this is an interactive object. We also need to know some of the physical properties, like the mass density, the hardness, and friction between this vase and the table and so on, in order to get a reasonable simulation, right? So how can we do that, right? Let me firstly show you an example, right? Here is just an image of different toolkits, right? For instance, for this type of, I hope that you are able to see my mouse. So for this type of materials, we might feel that it's sort of like soft, made of rubber, and have high friction for grip and so on and so forth. And for this part, it might feel that it's like maybe steel, and it could be quite dense and quite stiff and may conduct heat very well, right? So those are our intuitions, and we do have a very good intuition about understanding those physical properties, right? How do we actually do that? We actually recognize the material from our visual signal, and then based on our prior knowledge, we do have some prior knowledge associate physical properties with certain materials. This is why we human is able to do that. Then very naturally, we want to know whether GPT will also know physics. We actually ask these questions to GPT, and then GPT surprisingly gave us some reasonable answer. That basically convinced us, the large trained language models might actually encode some of prior knowledge into common material understanding, and that motivates us to build an automatic pipeline, allow us to encode physical properties from just visual input. So given still multiple images as input, we are able to do a 3D reconstruction, still build the scene representation as we discussed before. But what is different is we will train will basically encode some of the features. That features have been associated, have been trained to bridge the vision side and language side. That is called clip, and encodes some of the semantics. Say this region is more woodenish, and this region is more like rubberish, and so on and so forth. And then on the on the bottom, we also do some of the reasoning. So specifically, given the fact that this is a chair image, right? We'll do some automatic caption and to recognize what is the object. And based on the fact that it's a gray chair, we might also have a short list of potential materials that might be used to compose a chair, right? For instance, the different foam and wood and so on and so forth. And importantly, given all the materials, and we actually have a table of its corresponding physical properties. Like here we show a mass density. Where we can get that? We can get that from any appendix of a physics textbook, right? Those are just ground truths, right? We'll just link this clip feature with this big table of the fact of a material and their corresponding physical properties. And then what we'll do is just a very simple kernel regression. If this is more like woodenish, then we believe its physical property is also close to wooden's mass density, and we'll just use that to get a 3D physical property field. And in practice, it actually works very well in a zero-shot manner, meaning that we do not train any additional neural network. What we'll use is just large foundation models. So as you can see, it clearly distinguishes which part is likely to be more heavy, is likely to be more hard, and is likely to conduct more heat and so on and so forth. And by using this type of neural physical field, we are able to actually run a lot of physical simulations in our realistic game demo. And here is some of the car racing game. You can see that actually hit an existing car in the scene, and that will give us some more reasonable behaviors about the vehicle's collision and so on and so forth, because of the fact that we understand the physics. And next is another demo where we have an interactive agent that we control that agent to shoot out some balls, and those balls will hit the vase. The vase is already in that scene. It's just part of the video, but this vase is interactable now. We can actually shoot the vase down, right? One of the merits of having this simulation is not only about playing games, but also allow us to, do some robotics application. Here is an example. There we have mobile manipulators that interact with some of the existing objects on the table, right? Here we will grasp some of the dim sum from one place and rearrange to another place. So for the sake of time, I'm not going to go into more details about the evaluation, but essentially our video to game, our method is called video to game. Video to game can recover high quality geometry, can also render very well in terms of good PSNR and SEM and LPIPs. And in the meantime, what is important is we are able to run at interactive rate, with over 100 hertz at different platform with relatively low GPU and CPU usage. So if you are interested, you can definitely play the game by taking this QR code, and the source code is online, the demo is online as well. All right, so next I'm going to show, so far we have been, discussing about, different simulations in the digital world. And also we have been discussing about basically can we build a realistic and real-time simulation that, people and robots can play. So the next we are going to discuss about can we actually bring the simulation back to the reality. So here is one of our motivation. We want to evaluate how autonomy actually performs under, safety critical scenarios. For instance, whether this autonomy is able to break to J workers, or whether it will even break to J worker with occlusion, or whether it will handle the traffic violation situation and so on and so forth. That being said, many of these scenarios are quite safety critical, right? We don't really want to do a lot of this type of test in the real world before we make sure that our autonomy is safe. So we might actually refer to simulation, but traditional simulation is not realistic enough. So what we did before, around 3 years ago, is something called GeoSim. GeoSim allow us to take in one of the input video and then insert one of the reconstructed objects into the scene and simulate a realistic new video footage with this object conducting some of the safety critical behaviors. So here is a video footage of GeoSim. In this video, actually there are two vehicles that are fake. So one is on the left, this golf car, this Volkswagen Golf. The other is that white pickup truck that crossing the intersection. So both of the cars are simulated vehicles. So as you can see, this type of insertion rendering can give quite a realistic video footage so that we don't need to risk, our life in terms of evaluating those situations, but we can just simulate some of the safety critical behaviors. That being said, everything so far still stay in computer simulation, right? It does not really bring, real world hardware, real world physics, and real world mechanics into consideration. This is one of the drawbacks. It only evaluates from perception to motion planning, but for control side, which requires interaction with the real world, we do not have such a capacity. We can only evaluate at the perception and decision-making level. So in order to close this gap, we actually built something called Sim on Wheels. Specifically, as you can see here, we actually run an actual autonomy stack in real cars, but actually in an empty parking lot, as we can see in the middle. This is actually video footage that we have seen. But the vehicle has the sensory reading actually has been altered in a way that we run some oscillation on top of our sensory reading, so that it's like the vehicle has wear a pair of AR glasses. What it has seen is actually a safety critical scenario that the car is crossing the street, right? And then we'll test whether the vehicle is able to brake properly to the car which violates the traffic rules. So to based on specifically, right, based on the visual sensors, the vehicle will continuously obtain the images from the real world, and then under the nominal process, we'll just take those raw images and send to the autonomy. But we'll basically insert some of the safety critical situation and render that, and then get this render to the simulation interface. And that is our altered image, as we can see here. And we will send this altered image instead of the original image into the autonomy. And then we'll see whether this vehicle will take some actions here. So a good news about this is even if the vehicle will hit the pedestrian here, right, it's actually hitting a virtual pedestrian. What it will do is actually still drive in an empty street. It does not really bring any hazard. But what is nice here is it brings the entire physics and the mechanics and also the hardware in the loop. It has a real world latency, it has a real world physics, and so on. So only those hazardous or basically safety critical event is fake. Everything else is realistic. So this is one of the advantage of Sim on Wheels platform. So that essentially will close the loop. So here we show some examples. Here it is a pedestrian crossing case. As you can see from a third-person view, nothing in real world, but we simulate some of the virtual pedestrians crossing the street. Here is more challenging situations where some of the pedestrians are coming back from the occluders. As you can see, the reaction time for the vehicle is pretty short. In this specific case, it actually hits those pedestrians in its scenario testing. It didn't really pass this scenario, but there is no one get harmed. So we simulate all kinds of different diverse scenarios, and we also evaluate different autonomy pipelines, including monocular autonomy pipeline and also end-to-end reinforcement learning-based pipelines. And we also showcase that actually their behaviors are different across different scenarios, which I'm not going to more details. And one important part is how realistic your simulation is, right? We actually run some of the real world and simulation comparisons. We have a real world object placed in this in front of our vehicle. And we also actually render a digital replica, in front of the vehicle. And we compare, as you can see, that the gap is quite close, right? So the images looks quite similar. And here are different objects, and we also have our student to test. Basically, we build a digital twin of one of our PhD students who is also the first author of this paper, and then we render it properly, and we render his digital twin here, and then you can see that we get quite similar images in the end. So we can evaluate quantitatively, say, hey, this signal to noise ratio of these two images is roughly 20 dB, which sounds reasonable from a rendering perspective. But what does this imply? Does it imply this gap is smaller enough or not, right? So here comes actually important part that I would like to highlight. So whenever we do simulation, the real to sim gap actually will be propagated across our autonomy modules. For instance, if in the very beginning, our sensory side, like images, from image perspective, our real world scenario and the simulation, we have a gap like this. But after we pass to a perception module, which is a highly nonlinear function, right? Then in our state estimation part, we also have a gap in the state space. That gap might be actually changed to a highly nonlinear and potentially will be enlarged. And in the end, we also have a motion planning and control module. And then through propagate this uncertainty, in the end, we'll have a much larger or potentially a very different action space gap. In the end, what we care about sim to real gap is actually action gap. So long as we get simulation image, in the sense that after it passes through our autonomy pipeline, its resulting action are close enough, then we say this simulation can serve its goal to either validate or train our autonomy and as a substitute of a real world. So here we actually showcase that the action gap. We put a real world object here, and then we put a simulated digital twin here. Let's see in the end the behaviors, whether there are some difference. And we actually tested our sim-on wheel framework, and turns out that there might still result in some action difference. Specifically in this situation, the braking distance is roughly 0.5 meters off, which is actually not a small number. And we actually evaluate this type of reluctant gap from sensor to perception and to action. From sensor side, roughly 22 ps/h, but from perception, the mean intersection over union is roughly 84%. 84% is not like a very ideal number already. And in the end, for action, for of course, all kinds of different scenarios, our action endpoint offset in terms of braking distance is roughly 0.2 meters, which is also not quite good. And they suggest there are still a lot of stuff that we could potentially do in terms of close the sim to real gap. So we also evaluate. Sorry, what?
Can you tell what causes the gap?
What's
the reason of the gap?
What is the reason of this gap? The reason of that gap, actually, the initial cause of the gap is still coming from the fact that our digital replicas rendering is slightly different, slightly off of the reality. But one of the major cause of this gap is we pass this through a big neural network. That neural network is not very robust to small perturbations. Even if we have a very small perturbation, it might actually result in a very much different in action. This is quite similar to adversarial examples in neural network. This is what we conjecture that why it results in a larger action gap than the sensory side. And another reason actually results in a gap, actually, this is also something that I would like to discuss, is sim-on wheels on board will bring additional latency, right? Because we actually put simulation on board, and that will make our entire pipeline to be slightly slower. that will
That,
also
that
influence
one
our
is an
autonomy.
engineering problem, the latency. You can
Yes,
compensate it. The
exactly.
distortion from the neural net actually is a
That
big
is a
problem.
fundamental problem.
It's
Yes,
hard to fix.
exactly. Exactly.
Also, because I'm very interested, I think it's a wonderful work, and we are actually, we're in the same group. This is Louis. So
Yeah.
we are thinking about, we are doing the testing. So we try to use it, actually use the Shenlong wheel. So the feeling is, you are a team, yeah, you're doing superior work, but still you are not like a huge AI team. They
Yeah.
generate videos or things like that. So
Yeah.
if you compete on generating videos for Hollywood, then it's very hard to win. That's the size, the equipment. But they don't guarantee physical reality, so they are not suitable. They are very pleasing on the eye, but they are not suitable for doing safety critical signal view, right? Reduce the
Yes.
accident rate.
Yes. Yeah.
So the key difference is the compliance with physical reality. So
Yes.
that's the one. Um, so the question is, how can you make sure you can have error? That's always okay. For example,
Yeah.
even use a classical sensor, then you
Yeah.
have an error distribution, right?
Yeah.
Whatever sensor you have a error distribution. Once you have error distribution, you can compensate it. You can use Kalman filter, whatever. That's so the problem for AIs, sort of error distribution. It can be small, and then suddenly it can be totally unpredictable, become very
Yes.
bad.
Yes.
So the question is, can you constrain when you pass the big neural net? You have totally no constraint, or you can do something such that you can make an error bound, so to speak, or even
Yes.
probabilistic bounding. Make sure, is that possible?
Yes, yes, this is actually a very active research topic. It's not my core area, but this is called certifiable neural network or neural network verification. So actually, one of the researchers here at UIUC, Professor Wang from ECE, he has been studying that part, and I think in one of the next, this lecture series, he will basically discuss about that. So I do think nowadays there are some toolkits that we can use to make sure that neural networks error distribution is not going crazy.
Yeah.
So we can somehow constrain some of
Mm.
the properties of how the error has been propagated. So it's not ideally as a linear model for sure, right? Because the neural network still wants some capacity. In order to have more capacity, we have a highly nonlinear stuff, right? But the error could be somehow constrained, or we could estimate the error bound to be more precisely. That being said,
Also,
yeah.
I just want to mention something. For example, I work in aerospace a lot. So say turbulence. Nobody can have very accurate model for turbulence, right?
Yeah.
So what people do actually say you can choose a worst case path. So that means you're pessimistic.
Right. Yes.
So that would be useful. You will lose some
Yeah.
performance. So
Right,
can you
but it really
control and
depends
shift
on
the
how
error
loose about
distribution?
this. Yeah,
Can you
exactly.
kind of control and shift those error distribution, like people simulate turbulence for actually during the development and design for the aircraft wing.
Yes.
Now, nobody can generate. At the end of the day, you need to go to wind tunnel.
Yeah.
But even wind tunnel, it distorts. You have a wall, right? Wind tunnel has a wall. When you fly in the open space, there's no wall. So there's a
Yes.
wall effect. It's very hard to simulate. So even if you go to
Yes.
wind tunnel, it's still different from flying in the open space.
Yeah,
So
exactly.
any simulation, so wind tunnel is physical simulation. You blow the wind through tunnel, but the airflow is not quite the same in the open space.
Yes.
So what I try to say is those problems from the measurement to simulation for safety always exist. But
Yes.
they become useful if people can control the bug.
Yes. I
So
agree.
can you do that?
With the current toolkits, what I have seen so far is this is still a quite open problem because that worst case bound is very, very loose. It's it's so loose that it's not
Too
useful.
loose, too loose. No,
It's
they
too
can use it.
loose
So
that to be
now,
useful.
how the
Yeah,
people can do it in the classical simulation, say simulate turbulence or air, which is
yeah,
pretty nonlinear. So
yeah,
would
yeah.
there some lessons learned you can apply to here?
Yeah, I'm not 100% sure. I need to do more study on those type of wind tunnel simulation and see how people compensate. From my side, I do believe that as a simulator myself, as a simulation researcher myself, I do want to close this gap to be as smaller as possible so that error distribution will not be screwed up. But in the meantime,
Yeah.
as a
As long
people
as you
who,
can get control. I'm not saying I know how to do it, but I'll try to
yes,
say this
yes,
problem is
yeah,
not for you alone. Even in
right,
classical
right,
simulation, it already
exactly,
exists. So the
exactly,
question
yeah,
is there some transfer learning possible? I don't know. But now for
right.
more practical side is, can you add a LiDAR onto it? LiDAR return, like a Waymo,
LiDAR's
right?
gap, yes, I didn't really cover that much. I think one of the earliest LiDAR simulation, data-driven LiDAR simulation work is also coming from, some of my past work. And we actually demonstrate that LiDAR has a closer sim to real gap. It's not perfect, but it will be much closer than vision because LiDAR's physics is more or less to be better understood than the images, image physics.
Yes.
Yeah,
Because you have a partial physics model, say something, say
yeah,
10 meters or 20 meters ahead of you, right? So
yeah,
you get the parameter about a LiDAR. They actually give you a model about, and then certain
yeah,
surface reflectivity. So
yeah,
that
yeah,
actually a very similar, a very classical model can give you a simulated LiDAR return
yes,
because your vision already say they are person or whoever they are.
yeah,
But the LiDAR
yeah,
model is pretty accurate because it doesn't go for a whole neural net. Essentially, it's attenuation. So the surface,
exactly.
the
Yeah,
absorption from the color and material,
yeah,
as
yeah,
well as is a ring of thought. So that,
yeah,
well, all the models quite well. So it looks like that if you integrate that with that, then Waymo's express it can be used. We're actually using Waymo's track rapid publisher. And the Google car has a scanning radar on the top of the
yeah,
thing. So
yeah,
that means you cover that part. Now, one
yeah.
last question about how to use your thing we have is you have several camera mounted in different angle, right? Do you
Hmm.
support sort of the perspective thing when you talk about scene on reel? Scene on
Yes,
reel?
yeah, yeah. That can be handled very easily,
Oh, that can
and
be handled right away.
yeah,
So
yeah,
that's great. But the only
consistent
thing
across
missing is the
views. Yeah.
LiDAR.
Mhm.
How easy for you guys give a rough LiDAR? LiDAR.
Yeah, yeah. Actually, LiDAR is also straightforward. It's a known technique how to do that for insertion rendering. We didn't do that for the sake of, runtime, but that is something that we can integrate. The problem is the multimodal perception becomes a little bit more complicated if we do not rely on only LiDAR to build autonomy. If we rely on both LiDAR and the camera, then, because both sides will bring some of the gap, in the end, marrying the action gap will be more or less challenging. But I do agree with you
Yeah,
that incorporating
yeah.
LiDAR, given
The
the fact that
issue
its behavior is
is
better, yeah, we
actually
can. Yeah,
I,
yeah. Sorry, please
I
go
think
ahead.
it's easier than you think. You're thinking about the fusion
Yeah,
provide accuracy. So
yeah.
everything you said, I 100% agree. But a different perspective is like say everything has an error, right? Looks like Kalman filtering. Model has an error. Radar return an error. But
Hmm.
the error distribution is different. So you have
Yes.
way to integrate it. And in fact, you can put more weight for whatever reason.
Hmm.
So all you have to do is to let people do their own fusion, say Kalman filter fusion.
I
So you
see.
don't have so basically you just simulate independently, and then usually people have a bunch of sort of integration method from
Yes.
different
Yeah, I
perspectives.
agree. Yeah, yeah, yeah.
If you fuse it, then they have more trouble. So it's
Yes.
better to have it raw
Yeah,
and let them use whatever algorithm for their
yeah,
own fusion research. So if you add the LiDAR, so what we're trying to do is we integrate that. At least we try to integrate with the all the sensors seen Waymo publish. They're they're hundreds of thousands of miles, are very, very useful for safety.
Yeah.
But the whole difference you have Google don't provide is to let a virtual person jump into the road like you show. That is extreme variable because the Waymo track is just whatever it is, right?
Right. Yeah.
So and then you cannot construct those dangerous things, but that's precisely what the Waymo missing. So if you can superimpose on Waymo, then you will instantly have take advantage about the popularity of this Waymo, open Waymo sensor data.
Yeah.
So because you get the Oracle, you get the real data, and you see whatever the Google car sees. So that's very popular for people doing car simulation for safety. But they are missing what you have. Suddenly get somebody jump into the road or whatever, or a car cut in your front. So this feature is extraordinarily variable. And if you integrate Waymo, then everybody use Waymo will immediately use yours. And that number is huge.
Yes. Yes, I fully agree. Yeah. Thank you for the remark,
So
Louis. We should definitely
just,
chat offline
are you
more.
willing to do it? Because we are a Waymo track user. So are you willing to do it? If you're willing to do it, I will ask, actually, I'm one of, say, my postdoc to work with your student.
Yeah. Happy to follow up offline. And I know that I'm also run out of time. I may just quickly wrap up my talk, and then we can discuss more regarding the questions.
Yeah, I'll answer this. The feature you have really wonderful.
Yeah. Thank you so much. All right. So to summarize, today we discuss about combining data-driven methods and also physical-based knowledge to do modeling and simulation of the real world. So looking forward, we know that generative AI is here, and generative AI brings a lot of opportunities for creating new data, and that looks good. But at this moment, there are a few challenges. One is there is a lack of physical grounding, and there is also lack of precise control. Say, I want to place an object precisely in that location. Can you give me a corresponding, LiDAR data like what we just discussed with Louis? And also, they might not really follow, complicated instruction and so on. So this is what I will just quickly summarize about some of our ongoing work in order to make the data generation to be more, precisely controllable. Here we showcase some of the LiDAR generation. So all those results are purely generated from a generative model. But as you can see, we can get quite realistic LiDAR video footage. Actually, this layout simulator is actually coming from Waymo's WayMax simulator, but we will give them realistic LiDAR without actually collecting any one of the real LiDAR data assets. So here we also showcase some of our recent work that, is able to get physical grounded video results. On the left, we show some of the latest, greatest image to video generation algorithm. They have a lot of rich imagination, but it does not really grounded by any physics. On the right, we show that our simulation, which is looking more like a real world occurring situation. And here are some other examples like dominoes, or like some of the shelves and some of the small rigid body toys and so on. And for the sake of time, I also will quickly discuss, for some of the scenarios, say we want to simulate some of the very hazardous scenario, but we don't really have experts to write programs to do that, right? Can we actually make it as simple as like we just have a language instruction, say, I want to break the vase with a fireball, that we can directly give you some of the video footage like that, which is realistic and physical grounded. And for instance, some of the interesting cases like place 3 Pikachus on the table, or drop 5 basketballs on the table, and so on and so forth. So those are some of the ongoing work that we have been doing, and we look forward to discuss more, hopefully in future. And here is a summary of the project. And I would like to thank my student and also the funding agency. Sorry about being a little bit over time. I'm happy to take more questions now.
Thank you, Shenlong. Thank you. It was very interesting. Let's see if people have questions, because some of them left already.
Yeah, sorry
But
about
if there are questions, we'll take it. Right.
that.
Sorry, could you please tell a little more about the thing you mentioned at the very end? For example, place 3 Pikachus on the table.
Yes.
Are you planning to do something like controllable video generation?
Yes, we want to do controllable, not only just video, but controllable 3D or 4D scene editing and so on and so forth. For instance, like in some of the scenarios, we might want to simulate some of the hazardous experiment, like say post some of the entire neighborhood is post some of the fire hazard, right? So we might actually have some of the physical effects of the building is on fire, the car is on fire, and so on and so forth. There are a lot of debris on the street, and we want to actually simulate that. But we don't want, everyday user to write professional VFX code to do that. So what we do is we use large language model to link to some of the automatic code generation, and those code generation will generate some of the simulation code that depict some of the algorithms that we have written before, and then that algorithm can be run and give us some of the video footage like what I showed. Yeah, it's entirely physical driven, so it does not have hallucination issues like whatever those type of video generation model, which is purely data-driven model, will suffer from, right? Yeah.
Yeah, I see. So you basically you will have this like intermediate render.
Yes, exactly.
Oh, okay.
Yeah, intermediate render and physical simulator to actually generate and then augment into the video. So this is why we call it a VFX agent, because essentially it does VFX stuff, but without professionals using like Blender and using those type of VFX tools.
Okay. Is there a particular render you're using, or?
It can be generic, and so far that we have been using Blender's renderer. Yeah.
Sorry, if someone else has questions, go ahead, because I have another question.
Short question. Can you send an email to the contact? Send an email to me for your student working on Shenlong Reel.
For sure. Yeah.
Try to use it.
Yeah, I will
email and send to your student.
Yes, I will write an email to you and with my students who are working on that. Yeah. Mm-hmm. Yeah.
Michael, go ahead and ask your second question, so we close the meeting.
Yeah. I was gonna ask. So Blender has produces very realistic images, but it's not differentiable, and it's also quite slow.
Yes.
So is it a problem, or I mean, yeah, how are you gonna?
Yeah. At this moment, it's not really a problem for us because we don't need differentiability. All we are doing is forward simulation. That being said, if we want to actually in future improve realism or improve physical simulation realism, that we do need differentiable renderer and differentiable simulator. But the Blender simulator and renderer can be just an additional module that we can easily swap to Mitsuba, which is differentiable, or Taichi, which is differentiable physical simulator. Hooking up those is not really hard because essentially you just need to write some high-level wrapper of some Python script even Mitsuba and Taichi, they are also Python based. And what we have been written now is just Blender's Python script. We can just change that, and then the rest can work as a charm. And that being said, it's more like an engineering effort. I don't see a major obstacle that we cannot switch to differentiable renderer and simulator.
Okay, thank you.